Hello and welcome to this video. My name is Miss Simpson and I'm a Chemistry 20 teacher in Alberta. I'm going to, in this video, start a review of Science 10 chemistry that students need to build the foundational skills to be prepared for the lessons of Chemistry 20. So we will get started by reviewing WHMIS really quickly. So anytime you have a lab situation, you're using chemicals, we're going to be seeing WHMIS symbols on our materials. Now, WHMIS stands for Workplace Hazardous Materials Information System, and in 2015 they realigned it to align with a globally harmonized system. WHMIS tells us how to handle, store, and dispose of reactive materials. It usually comes in a symbol format that tells you kind of a quick glance what hazards are associated with it. But if you want complete information on the chemical, you're going to find something called a safety data sheet, SDS for short. Safety data sheets have complete information on the hazardous product that you're dealing with. So these are your WHMIS 2015 symbols. Okay, we have exploding bomb for explosion or dangerously reactive hazards, the flame for any fire hazards, flame over circle for oxidizing hazards, meaning they react with oxygen, such as rusting and corroding, things like that. Gas cylinder for a gas under pressure. Corrosion is one of the more common ones you're going to see when we're dealing with chemicals in Chem 20. They can be slightly corrosive depending on how concentrated they are, so we wear safety goggles, we may wear gloves depending on how corrosive our solutions are. Skull and crossbones can cause death with short exposure, so that's obviously definitely something you don't want to drink. Same with health hazard and exclamation mark. They also can cause health effects, and exclamation is less serious than skull and crossbones or health hazard, but still something you want to obviously not drink or release into the environment, as it says it can damage the ozone layer. And then environmental damages, things we definitely don't want to put down the sink because it can affect the aquatic environment. Those are the main chemistry ones you'll see with the red triangles or diamonds, I guess, around them. But biohazardous is another one that you might see that can contain diseases from people or animals, like on needles and things like that. Not commonly something you'll see in the chemistry lab. So the periodic table is like very, very, very important in chemistry, right? It has all the information we need whenever we're doing multiple different types of questions and calculations and all sorts of things. So the periodic table was developed by Mendeleev, and you are always given a periodic table on every test and quiz. So there are, on the modern periodic table, 118 elements currently. So when you're looking at the periodic table, we can talk about the different periods and the different groups. So the periods are the horizontal rows. Okay, there are 7 in total. When you're looking at your periodic table, the lanthanide and actinide series at the bottom, I think I have an image in the notes. They've been removed to make the periodic table fit on a page, but they're actually part of the last 2 periods. So there are 7 periods in total, 7 rows or 7 periods. Okay, periods, sorry. Groups and families are the vertical columns. There are 18 in total, and they have different numbering systems. Old numbering systems used to use A's and B's. We focus mainly on just the numbers 1 to 18 for our modern periodic tables. Some of the groups or families have common names. So group 1, for example, are called your alkali metals. They are the most reactive metals on the periodic table. Now, when we look at a periodic table, remember there's a staircase line, and everything on the left of the staircase line is a metal, everything on the right is a non-metal. So group 1 being part of the metals, the alkali metals are most reactive. Group 2 are the alkaline earth metals. They are the second most reactive metals. In Science 10, we talk about the reactivity of the periodic table of elements on the periodic table. Metals are more reactive as you move to the left and go down. So francium being the most reactive metal. Non-metals, on the other hand, which group 17 is part of, these are the halogens. These are your most reactive metals. Sorry, non-metals. And non-metals become more reactive as you move to the right and go up. So fluorine is the most reactive nonmetal because the noble gases, group 18, are unreactive. Sometimes you'll hear them as being called inert. This means they are unreactive. Now, unreactive, I might be spelling this wrong, but unreactive means it's stable. We're going to talk today about why noble gases are stable and they do not react. Okay, so here's a nice image of the periodic table. Okay, this is our staircase line. Everything again on the right-hand side is the nonmetals. Everything on the left are the metals. And the metalloids, they've been removed from these two periods here. This is for the lanthanide series, usually the first elements that's been removed. And the second one is for the actinide series, the first element that's usually removed, depending on your periodic table. Your periodic tables in the Alberta curriculum actually removes a couple of different elements as the first elements in those series. It leaves lanthanide and actinide, or lanthanum and actinium on the periodic table, and it removes cerium and thorium. Either way, though, it's still just trying to shorten the periodic table into one page. But those bottom ones are usually called the lanthanide or lanthanum series and the actinium series. They are still metals. Now, along the staircase line, we have metalloids. Metalloids are just elements that have properties maybe of both sides of the periodic table because metals and nonmetals, which we'll review right now, have different properties. So the properties of metals is they are ductile. Ductile means you can stretch them into a wire like copper. They're lustrous. Lustrous means they are shiny. They conduct heat and electricity. They are malleable. I think of a mallet for malleable. You can pound them into a thin sheet like aluminum foil. They are on the left-hand side of the staircase and make up approximately 80% of the elements on the periodic table. Now, nonmetals, on the other hand, are basically all opposites. They are not ductile, they're brittle, they're dull, they do not conduct, or if they do, very slightly. They're found to the right of the staircase line and make up the other 20% of the elements on the periodic table. Now, as I mentioned, metalloids are some of the elements that are along the staircase line that can have properties of both sides. So carbon, for example, carbon is actually a nonmetal, but it conducts. And so that's something that normally a nonmetal cannot do. Silicon also being a nonmetal, but it's lustrous or shiny, which again is usually not something a nonmetal can do. You don't really have to know which elements are metalloids. They're still either a metal or a nonmetal. It's just if it's asking you a question of why does carbon conduct even though it's a nonmetal, it'd be because it's considered a metalloid. Okay. Reviewing atomic structure. So if you remember, when I have an atom, there's several definitions of atoms or an evolving theory of atoms that you learn about in Science 10, but we're going to essentially think of the Bohr model, where we have a nucleus in the center of the atom, and the nucleus contains the protons and the neutrons, and the electrons are orbiting around the nucleus, kind of like a solar system model. So my electrons, again, are going to be found in this external area to the nucleus. So these are our three subatomic particles: neutrons, protons, and electrons. Now, neutrons have a charge of 0. They do not carry a positive or negative charge. So you'll see a little not symbol there, meaning they do not carry a charge. Protons, on the other hand, are positive, so you'll see a little positive symbol with them, and electrons are negative, so you'll see a negative symbol associated with them. Now, their masses. Do you need to know the mass of an individual subatomic particle? No, you don't. But what's key to know is that protons and neutrons have the same mass. Okay? Whereas electrons have a much smaller mass. So what this means is when I'm trying to determine the mass of an atom, I'm only taking into account the protons and neutrons. We're assuming that the electrons are essentially massless. They do not contribute, to the mass of the atom. The mass comes from the nucleus, and the nucleus again contains only protons and neutrons. The electrons, however, they are found in this cloud region. The quantum mechanic theory is the most modern theory we have for atoms and how these electrons are statistically where you're likely to find them. But we can simplify it, like I said, using the Bohr model or the solar system model to the electrons orbiting around the nucleus. This makes up the volume, the majority of the volume of the atom. I saw in a video somewhere that if you had a football field the size of an atom, the nucleus would only be a spider in the football field. And it might even have been multiple football fields. I can't remember exactly. But the nucleus contains the mass but is very, very small in the middle. The majority of the size or volume comes from the cloud region where the electrons are found. And we will look today at how to draw what we call energy level diagrams representing an atom. Now, before we get into that, we're going to bring up isotopes and what it means to have an isotope and how you figure out the number of subatomic particles that your atom has. So first of all, when you're looking up the mass on the periodic table, that's called the atomic molar mass. So if I were to look up sodium's atomic molar mass is 22.99. The units can be written as atomic mass units or grams per mole. Either way, when I use this number, I'm going to round it to get what we call the mass number. So the mass number for sodium would be 23. That means that my number of protons and number of neutrons is going to add up to 23. Okay? Now, the number of protons, when you're trying to find the number of protons that an atom has, it is always the atomic number of an atom. Sorry, sometimes my pen makes these lines while I'm writing. It is the atomic number. So if I were to, I'm going to draw down here for a sec. If I were to look up an element on my periodic table, let's look up sodium, as I just mentioned. You'll see the symbol for sodium written like that. You'll see the name sodium written below. And then there's a bunch of numbers. There's an 11 on the top corner and a 22.99 on the other corner, as well as some other numbers, but I'm just going to end at those two numbers. This number on the top right-hand side was the atomic molar mass, and this is your atomic number. Okay, so what that means is that sodium has 11 protons. Okay, now we know that protons and neutrons equals the mass. So if I rearrange to solve for neutrons, the number of neutrons I have is going to be the mass number, which is again the rounded mass, minus the number of protons. So for sodium, if I had a mass number of 23 and I have 11 protons based on the atomic number, that means I have 12 neutrons. Again, the protons and neutrons making up the nucleus. For isotopes, this is important because what an isotope means is that you have two different forms of an atom. They have different masses. Why do they have different masses? It's not because of the protons. Protons is always atomic number. So they have the same number of protons, but their masses are different because they have a different number of neutrons. Okay, so for example, we're going to look at carbon. So if you find carbon on your periodic table, when you look up the atomic mass of carbon, on the periodic table it says 12.01. That's the average mass of all of the isotopes of carbon. Each individual carbon atom can have a different mass. That 12.01 is the average. Okay? So when you're given the name with a number after it, this number is the mass number that it's giving you. It's telling you you have carbon with a mass of 12 versus carbon with a mass of 14. How do we figure out their subatomic particles? So carbon's atomic number is 6. So that means carbon is going to have 6 protons for both isotopes. But their neutrons are going to be different. Okay? For carbon's neutrons, it's going to be the mass number of 12 minus the protons, which is 6. There are 6 neutrons in carbon 12. But in carbon 14, to find my neutrons, this time my mass is 14. So when I minus the protons, this time I get 8 neutrons. Okay? So they have the same number of protons, but a different number of neutrons, which gives them different mass numbers and makes them isotopes of each other. Now you will also see something called isotope notation. Isotope notation is a shorthand form of showing you the two different isotopes that you may be comparing. Isotope notation is always X, which is going to be the symbol of the element. So for example, for my carbon-12, that would be a C. The A is a number written to the top left-hand side of the symbol, which is the mass number. So for carbon-12, it would be a 12. And then Z is a number written at the bottom left-hand side, which is the atomic number, the number of protons. So for carbon-12, that would be a 6. Okay, so the isotope notation for carbon-12 would look like as follows. For carbon-14, it would be very similar. It would be C, but with a 14 on the top and a 6 on the bottom. Okay, so let's look at an example. Let's say you're told you have copper 64 and copper 62. Now, if you remember back to Science 10, elements can come in two forms. They can either be an atom or an ion. We're going to talk about ions in the next lesson, but for today we're focusing on atoms. If it doesn't tell you whether you have an atom or an ion, you can always assume it means you have an atom. Now, what is the difference between them? Atoms are electrically neutral. So that means when you have an atom, the number of electrons is always going to equal the number of protons, so that those positive and negative charges balance, and you have an electrically neutral particle, which is your atom. Okay? Ions have a different number of electrons than protons, so they have a net charge, but we're not going to talk about that right now. We'll talk about that in the next lesson. So assuming we have atoms, that means, again, to figure out my electrons, it equals my protons. All right? So first of all, what is the isotope notation of copper 64 going to look like? We're going to have a Cu as my symbol for copper. The 64 means that's its mass number, so I put that on the top left. And what is the atomic number? So find copper on your periodic table. It's in group 11, period 4. The atomic number for copper is 29. Okay, so for this copper 64 isotope, remember the number of protons is the atomic number. And the atomic number we just discovered was 29. The number of electrons equals the number of protons, which is also therefore 29. And then the neutrons is the mass number minus the protons. So that would be 64 minus 29, which would be 35. So if I actually put a little symbol after this, I have 29 protons, 29 electrons, and 35 neutrons in an atom of copper 64. Okay? Pause the video and try copper 62 as an atom and see if you can get the answer. So my isotope notation has my Cu symbol for copper, 62 this time on the top left, and still 29 on the bottom, because again, the atomic number is always the same for isotopes. So a copper atom has 29 protons. Again, that was atomic number. It'll also have 29 electrons because they're the same in atoms. And the neutrons this time would be 62 minus 29. I believe that is 33. I'm not using my calculator here. I should, but I believe that is 33 neutrons. So my copper 64 and copper 62 have the same protons and electrons. They're the same element, but they have a different number of neutrons contributing to them having a different mass. And you can see there how their isotope notation differs. Okay? So that's really the majority we're going to spend on isotope notation. What we're going to look at now is drawing what we call an energy level diagram. This is a representation. Energy level stands for the electron orbitals that the electrons are moving around in. Okay? In Science 10, you may have heard these called EELRs. That stands for electron energy level representation. This is the same thing. You're trying to show the atomic structure of an element. Okay? We're, like I said, going to focus today on atoms, the atom form of an element, which are electrically neutral, again meaning the number of protons equals the number of electrons. Now, when you're drawing the energy level diagram of an atom or an ion, which we'll talk more about tomorrow in the next lesson, you're going to start with a nucleus. The nucleus, like I said, is in the center of your atom, and you're actually going to put the protons and the neutrons in the nucleus, the exact number that you have for that element. Then your electrons are orbiting around in these different energy levels or orbitals. Now, when you're distributing your electrons, there's a maximum number that each level can hold when you're distributing them, and you always start at the nucleus, the energy level closest to the nucleus. So the first energy level can hold a maximum of 2 electrons. If your atom has more than 2 electrons, you're going to then put them in the second energy level, which can hold a total of 8 electrons. The third energy level, if you still have more electrons, you go to put them in the third. That can also hold a total of 8 electrons. Now, if you still have more electrons, you'll put them in the next level, which can hold a maximum of 18. Now, this can actually continue on and on and on, up to 7 levels, each level actually representing the number of elements in the period. So our first period on the periodic table has 2 elements. It can also hold 2 electrons. Second and third level have 8. Fourth and fifth would have 18. Sixth and seventh would have 32. We're not going to go that far, but that's a way to remember how many electrons each energy level can have. Okay? So you need to memorize these maximums up to the 4th level, probably for Chem 20 would be enough, to help you, again, distribute your electrons when you're drawing the energy level diagram of a substance. So let's do some examples. Let's look at sodium and lithium. So when I'm doing these examples, I'm starting with, I need to look up my atomic number and the mass number of my atom. I have sodium. We looked at sodium already, but a reminder that the atomic number is 11. Remember, the mass number is the rounded mass. So if I look it up, it's 22.99. That's going to round to 23. Okay? So what this means is my subatomic particles. Just a reminder here, your protons equals your atomic number. When you have an atom, your electrons equals your protons, and neutrons are always mass number minus protons. Okay? So for sodium, this here is what I start with in my diagram. This represents my nucleus. And inside my nucleus, I need to put how many protons and how many neutrons an atom of sodium has. So if sodium's atomic number is 11, it'll have 11 protons in the nucleus. If the mass is 23, remember to find neutrons, I take the mass and minus the protons. So my neutrons, I'll just do a little calculation down here, is 23 minus 11, which gives me 12. So in my nucleus, I'm going to write beside my neutrons that there are 12 neutrons inside the nucleus. This circle represents the nucleus. Now, the number of electrons I'm going to have is equal to the number of protons, which is 11. Now, my electrons, like I said, are not inside the nucleus, so you don't put electrons in here. You don't do that. The nucleus only contains the protons and neutrons. The electrons are orbiting in these circles around the nucleus. Now, drawing an entire circle is just kind of a waste of time, so we never draw an entire circle. We just draw either a curved line to represent that energy level or even a straight line. A straight line is fine too. Okay, but these represent the energy levels where the electrons are found. Now, I have 11 electrons in total. okay? But I can't just put them all in the first orbital. Remember, the first orbital can only hold a maximum of 2 out of the 11 that I have. So I fill up that first orbital, and then I need to go to the next orbital to put more electrons. Now, if I put 2 already and I have 11, that means I have 9 more. But again, the next energy level cannot hold 9. It can only hold 8. So I'm going to put 8 electrons in that energy level, and then I need to add a third energy level. And this is where I'll put my final electron so that I have a total of 11 electrons making up the energy level distribution for my energy level diagram. Okay? So those are my 11 electrons, 2, 8, and then 1. Now there's some important summaries that we can make, or checks that we've done this correctly. The energy level furthest from the nucleus is called the valence energy level. And this will come up important in the bonding unit, okay? My valence level here has 1 electron in it. That corresponds to the period that that element is on in the periodic table. Sodium is in period 1. That corresponds, sorry, I lied. That's supposed to be group. The group sodium is in, not the period. My bad. Okay, sodium is in group 1. It has 1 valence electron. When we get into the bonding units and we look at how things bond to each other by sharing or transferring electrons, we're going to want to know their valence electrons, because that's the only level that's unfilled. The inner levels are filled. And so in order to figure out how many valence electrons something has really quickly, I can just look up its group number. Its group number tells me how many valence electrons it has. Now, the periods, that's where I was going. The periods come from the number of energy levels you have electrons in. I have 3 energy levels, and those 3 energy levels are orbitals, correspond to the period that the element is in, okay? So my sodium being in period 3 has 3 energy levels. That's kind of just a check for you after you draw your energy level diagram, to check and make sure that you have the electrons distributed appropriately. Okay? Let's look at lithium as our second example. So again, I start by looking up the atomic number. The atomic number for lithium is 3. And the mass number, so if I look up the atomic mass on the periodic table for lithium, again, if you can't find lithium, it's in group 1, period 2. The atomic mass is 6.94, so that's going to round to 7, okay? So again, I already have these circles drawn because I can't draw circles very well, but I draw a circle to represent my nucleus. And again, in my nucleus, I'm going to say how many protons and how many neutrons there are. Okay, so the protons again are the atomic number. My atomic number is 3. So I have 3 protons in an atom of lithium. My neutrons are also in the nucleus. Mass minus mass number, which is 7, minus protons, which is 3, gives us 4. There are 4 neutrons in the nucleus. And then last are my electrons. Those again are in the energy levels surrounding the nucleus. I am going to have the number of electrons for an atom equaling the number of protons, which again is the atomic number, which is 3. So now to draw my electrons, again, I start with the energy level closest to the nucleus and I fill it up. It can only hold 2 of my 3 electrons. So I then have to add another energy level, put my last electron in there, and then I'm done. I add this up to show that these are my 3 electrons. 2 in the first energy level, 2 in the first energy level, 1 in the second energy level. Okay? So again, my valence electron is 1, and that's the group that lithium is in, group 1. And the number of energy levels, there are 2 energy levels. That corresponds to the period that lithium is in, period 2. Okay? So a check for yourself after you've drawn it to make sure you've drawn it correctly. Oops, I accidentally erased one of my energy levels. Sometimes students will draw little little circles like this to represent the electrons. Some teachers allow that. I allow it as well, but you also need to put the number off to the side because I don't want to sit there and count how many electrons you have drawn. So always put the numbers off to the side. Okay? And I believe, I'm just going to erase this and double check that this is the end of today's lesson. It is. Okay? So there again are your energy level diagrams, what they should look like for sodium and lithium atoms. Next lesson we will review ions. Thank you for watching this video.